Today, we're going to explore 5 scientifically grounded practices that can help you not only look younger, but feel younger at the cellular and neurological level. These aren't gimmicks. They're rooted in biology, circadian science, and behavioral neuroscience. Sleep is not merely a passive state of rest. It is one of the most metabolically active and regenerative periods in our 24-hour cycle. During deep non-REM sleep, a number of critical physiological processes take place that directly impact how we age, both externally in terms of skin, posture, and appearance, and internally, including cellular repair, hormone regulation, and cognitive function. One of the most important mechanisms active during deep sleep is the secretion of growth hormone. This hormone plays a major role in stimulating tissue repair, muscle recovery, and the maintenance of youthful skin by enhancing collagen production. Collagen is a structural protein that gives skin its elasticity and firmness, both of which decline with age and sleep deprivation. Sleep also activates the glymphatic system, a recently discovered waste clearance pathway in the brain. This system is most active during deep sleep, especially in the early hours of the night. Its primary function is to remove neurotoxins and metabolic waste products that accumulate during waking hours. Inadequate sleep impairs this system, leading to cognitive fog, slower reaction times, and over time, a higher risk for neurodegenerative diseases such as Alzheimer's. From a cosmetic standpoint, poor glymphatic clearance contributes to puffiness, dull skin, and a tired appearance, which collectively signal accelerated aging. Furthermore, sleep deprivation alters levels of cortisol, the body's primary stress hormone. Chronic elevation of cortisol degrades collagen, thins the skin, and promotes abdominal fat accumulation, all of which are markers commonly associated with aging. Lack of sleep also reduces the body's insulin sensitivity, which not only promotes fat storage, but contributes to skin glycation, a process where sugar molecules attach to collagen and elastin, leading to stiffness and premature wrinkling of the skin. These biological effects often begin subtly, but over weeks, months, and years, they manifest visibly and systematically. From a circadian biology perspective, timing is just as crucial as duration. The human body is governed by a roughly 24-hour internal clock known as the circadian rhythm, which is heavily influenced by light exposure. Aligning sleep with this rhythm enhances hormonal cascades, particularly melatonin and cortisol, which orchestrate sleep onset and immune recovery. Melatonin is not only a sleep-promoting hormone, but also a potent antioxidant, helping to neutralize oxidative stress that contributes to cellular aging. Disrupting this rhythm by staying up late under artificial light or waking at inconsistent times dampens melatonin production and impairs the restorative effects of sleep. Consistency in wake and sleep times has a cumulative effect. Research shows that even a single night of disrupted sleep can negatively alter gene expression, particularly genes involved in inflammation, immune function, and stress response. Over time, these disruptions accumulate, promoting systemic inflammation, insulin resistance, and mitochondrial dysfunction, all key hallmarks of aging. Setting a consistent wake time anchors the rest of the circadian system and makes it easier to fall asleep at night without the need for stimulants or sleep aids. It also trains the brain to expect and prepare for rest, reinforcing deeper, more efficient sleep cycle. Exposure to natural sunlight, particularly in the early part of the day, is one of the most powerful and underutilized tools for optimizing human health and slowing the aging process. Light is not just something we see with, it is a biological signal that calibrates our entire body's internal timing system, known as the circadian rhythm. This rhythm governs virtually every physiological process, including hormone secretion, metabolism, immune function, and cellular repair. When we expose our eyes to sunlight in the morning, specifically within 30 to 60 minutes of waking, it sends a powerful signal to the brain's master clock, the suprachiasmatic nucleus located in the hypothalamus. This signal sets the phase of the circadian rhythm and initiates a cascade of downstream effects that promote wakefulness, mood stability, and energy during the day, while also ensuring better sleep quality at night. Morning sunlight exposure triggers the release of cortisol in a healthy, natural spike. Cortisol is often misunderstood as solely a stress hormone, But when it follows its natural rhythm, rising in the morning and tapering off in the evening, it plays a key role in alertness, metabolism, and fat mobilization. This natural spike is entirely different from chronic cortisol elevation due to stress or poor sleep. When cortisol rises appropriately in the morning, it helps regulate inflammation and supports cognitive function throughout the day. Disrupting this pattern, for example, by staying indoors under artificial lighting, flattens the cortisol curve and can lead to increased fatigue, irritability, and poor metabolic regulation. Another crucial effect of early light exposure is the suppression of melatonin, the hormone that makes us feel drowsy. Melatonin is produced by the pineal gland and typically begins rising in the evening as light diminishes. By exposing ourselves to bright natural light in the morning, we effectively shut off residual melatonin from the night before, helping us feel more alert and better aligned with the day's rhythm. This timely suppression also sets a timer for melatonin's re-release, approximately 14 to 16 hours later, allowing it to rise at the correct time and support deep, regenerative sleep. Importantly, the spectrum and intensity of natural light, especially blue light components, are far stronger than those found in indoor environments. Even on a cloudy day, natural light delivers hundreds to thousands of lux of intensity compared to indoor lighting, which often falls below 500 lux. This intensity is what makes natural light biologically potent in regulating circadian timing. Inadequate light exposure, particularly in the morning, leads to circadian desynchronization, which has been associated with premature aging, poor sleep, mood disorders, weight gain, and increased risk for chronic disease. On a cellular level, circadian alignment through morning light helps regulate the timing of mitochondrial activity. Mitochondria are the energy-producing organelles in cells, and their efficiency impacts how well our cells function and repair. When mitochondrial rhythms are synchronized with light-dark cycles, cells are more effective at handling oxidative stress, producing ATP, and carrying out autophagy, all essential to slowing down the cellular hallmarks of aging. Cold exposure, when used deliberately and consistently, activates a cascade of physiological responses that can reduce inflammation, improve circulation, enhance skin tone, and ultimately contribute to a younger and more resilient appearance. The practice involves exposing the body to cold temperatures for short durations. This can be through cold showers, ice baths, or even facial immersion in cold water. One of the most immediate effects of cold exposure is vasoconstriction, the narrowing of blood vessels near the skin's surface. This helps the body retain heat, but when followed by a return to normal or warm temperatures, vasodilation occurs. Blood vessels expand again, leading to enhanced blood flow. This dynamic contrast improves circulation to the skin and extremities, which contributes to a healthier complexion and improved nutrient delivery to the skin's surface. Another major benefit of cold exposure is the modulation of inflammation. Chronic low-grade inflammation is a key driver of aging and age diseases, including cardiovascular disease, metabolic syndrome, and even neurodegeneration. Cold exposure reduces levels of pro-inflammatory cytokines while increasing the availability of anti-inflammatory molecules. This downregulation of systemic inflammation not only supports joint and muscle recovery, but also promotes clearer, healthier skin and improved immune regulation. By repeatedly exposing the body to short-term cold stress, the nervous system becomes more efficient at handling environmental and emotional stress, contributing to overall resilience. Cold exposure also triggers the release of powerful neuromodulators, namely norepinephrine and dopamine. Norepinephrine increases focus, alertness, and energy, while dopamine contributes to feelings of motivation and well-being. These chemicals are part of the body's natural reward system, and their release during cold exposure can lead to enhanced mood, improved mental clarity, and increased willingness to engage in other health-promoting behaviors. Repeated cold exposure, even as little as 1 to 3 minutes per session, leads to lasting increases in baseline dopamine, which has implications for cognitive performance and stress resilience, factors that contribute to maintaining youthfulness at the behavioral and neurological level. In terms of metabolic health, Cold exposure stimulates brown adipose tissue, a type of fat that is metabolically active and burns energy to produce heat. Brown fat activation has been linked to improved insulin sensitivity, better glucose metabolism, and enhanced fat oxidation. These metabolic effects help reduce visceral fat accumulation, one of the hallmarks of metabolic aging. Visceral fat is not just a cosmetic issue. It releases inflammatory molecules that damage organs and accelerate aging processes throughout the body. Increasing brown fat activity through regular cold exposure can counteract these effects and support a leaner, more youthful physique. On a cellular level, cold exposure induces a mild hormetic stress response, meaning it challenges the system just enough to provoke an adaptive, strengthening reaction. This process includes the upregulation of heat shock proteins and cold shock proteins, which assist in cellular repair, protein folding, and protection against oxidative stress. These proteins play a vital role in maintaining cellular integrity and slowing age decline in mitochondrial function. Hormetic stress, like cold exposure, teaches the body to become more efficient at maintaining balance, which is central to slowing aging across multiple systems. Resistance training is one of the most effective strategies for reversing biological aging and maintaining a youthful appearance, both physically and physiologically. While commonly associated with building muscle and strength, the benefits of resistance training extend far beyond aesthetics. On a cellular level, resistance exercise promotes mitochondrial biogenesis, the creation of new mitochondria within muscle cells. Mitochondria are the energy factories of the cell, and their efficiency determines how well cells function, repair, and defend against oxidative stress. As we age, mitochondrial function naturally declines, contributing to fatigue, poor metabolic health, and cellular aging. Regular resistance training can slow or even reverse this process by enhancing mitochondrial density and improving energy metabolism throughout the body. Muscle mass itself plays a critical role in healthy aging. Muscle acts as a glucose sink, helping to regulate blood sugar levels and improve insulin sensitivity. This reduces the risk of type 2 diabetes, metabolic syndrome, and other age conditions driven by poor glucose regulation. Importantly, muscle is also a highly active endocrine organ. It releases signaling molecules known as myokines during contraction, which have systemic anti-inflammatory effects. These myokines improve immune function, support brain health, and combat the chronic low-grade inflammation that accelerates biological aging. Through this mechanism, muscle serves as both a structural and biochemical defense against age decline. Resistance training also supports the production of anabolic hormones, including testosterone and growth hormone. These hormones naturally decrease with age, but they are essential for maintaining bone density, muscle mass, skin elasticity, and libido. Engaging in regular strength training helps sustain optimal hormone levels without pharmacological intervention. Compound movements such as squats, deadlifts, and presses stimulate large muscle groups and create a hormonal environment conducive to growth and repair. When paired with adequate protein intake and recovery, these exercises support tissue regeneration and overall vitality. From a neurological standpoint, resistance training enhances brain health and cognitive function. It increases brain-direct neurotrophic factor, BDNF, a protein that supports the growth and maintenance of neurons. BDNF is closely linked to memory, mood, and long-term brain plasticity. Higher levels of BDNF are associated with slower cognitive decline and a reduced risk of neurodegenerative diseases such as Alzheimer's. Resistance training also improves coordination, balance, and proprioception, which are essential for maintaining independence and reducing injury risk as we age. On the surface level, strength training contributes to posture, joint stability, and skin tone. With age, muscles naturally atrophy, a process known as sarcopenia, and connective tissues weaken, leading to frailty, a hunched posture, and a tired appearance. Resistance training combats this by reinforcing muscle architecture and tightening the structures that support skin and skeletal alignment. Even modest gains in muscle tone can lead to noticeable improvements in physical presence, giving the body a more youthful, confident look. Training just 2 to 4 times per week, focusing on progressive overload and recovery, can yield significant anti-aging benefits across nearly every major system of the body. Intermittent fasting is a dietary strategy that leverages the body's natural metabolic and cellular processes to promote health, longevity, and youthful function. Unlike traditional dieting, intermittent fasting focuses not on what you eat, but when you eat. By restricting food intake to specific time windows, typically ranging from 8 to 12 hours per day, you activate internal repair mechanisms that are otherwise dormant in a constantly fed state. One of the most powerful processes triggered by fasting is autophagy, a cellular housekeeping function in which cells identify and recycle damaged components. Autophagy plays a crucial role in reducing oxidative stress, preventing the accumulation of dysfunctional proteins, and promoting cellular renewal, all of which are key factors in slowing the aging process at a cellular level. In addition to autophagy, intermittent fasting has a significant impact on mitochondrial function. During fasting, the body switches from glucose to fat as its primary energy source, entering a state known as ketosis. In this state, cells burn fatty acids and ketones, which are cleaner fuels that generate fewer reactive oxygen species compared to glucose metabolism. This reduction in oxidative stress protects DNA, reduces inflammation, and supports mitochondrial efficiency, benefits that translate into improved energy, sharper cognition, and slower aging of both the body and the brain. The metabolic switch also improves insulin sensitivity, helping cells respond more efficiently to insulin and reducing the risk of insulin resistance, which is a major driver of age diseases such as type 2 diabetes and cardiovascular conditions. Fasting also affects key hormonal pathways that influence aging and longevity. Human growth hormone, HGH, levels can increase during fasting periods, supporting fat metabolism, muscle preservation, and tissue repair. Insulin levels, on the other hand, remain low during fasting windows, promoting lipolysis and reducing the inflammatory effects of high circulating insulin. Together, these hormonal shifts create a metabolic environment that favors cellular repair and efficient energy use rather than fat storage and degeneration. Additionally, fasting improves leptin and ghrelin signaling, the hormones responsible for satiety and hunger, leading to better appetite control and reduced overeating, which are critical for maintaining a healthy body composition over time. On the genetic level, intermittent fasting influences the expression of longevity associations, including those involved in stress resistance, DNA repair, and cellular maintenance. Fasting activates sirtuins, a family of proteins that regulate cellular health, inflammation, and metabolism. Sirtuins also play a role in telomere maintenance, structures at the ends of chromosomes that protect DNA and shorten with age. By supporting telomere integrity and reducing DNA damage, intermittent fasting may help preserve genomic stability, one of the core mechanisms of longevity. Psychologically, fasting can enhance clarity, mood, and emotional regulation. The neurochemical changes associated with fasting, such as increased production of norepinephrine and brain-directed neurotropic factor, support synaptic plasticity and mental sharpness. These effects improve focus and resilience, traits often associated with youthfulness. Importantly, these cognitive benefits are not temporary, but become more pronounced with consistent practice. Even adopting a simple 12-12 fasting window, where eating is confined to a 12-hour period each day, can initiate many of these regenerative pathways without requiring extreme dietary changes or caloric restriction. Minimizing ultra-processed foods is one of the most direct and impactful strategies for slowing aging and improving overall health. Ultra-processed foods are not just unhealthy because they are high in sugar, salt, and unhealthy fats. They also contain a wide array of synthetic additives, preservatives, emulsifiers, artificial colors, and flavors that disrupt the body's natural metabolic processes. These foods are engineered for maximum palatability and shelf life, but are devoid of the micronutrients, fiber, and phytochemicals that are essential for cellular repair, immune function, and metabolic balance. Consuming these products regularly contributes to chronic low-grade inflammation, a key driver of aging and virtually every major age disease, including heart disease, type 2 diabetes, cognitive decline, and certain cancers. At a cellular level, the refined carbohydrates and added sugars found in ultra-processed foods lead to spikes in blood glucose and insulin. Over time, these repeated spikes cause insulin resistance, one of the earliest signs of metabolic dysfunction. Insulin resistance not only increases the risk of diabetes, but also accelerates skin aging through a process known as glycation, where sugar molecules bind to collagen and elastin fibers in the skin, making them stiff and prone. This results in the loss of skin elasticity, fine lines, and wrinkles. Glycation also promotes systemic inflammation and oxidative stress, both of which contribute to the breakdown of cellular structures and DNA. Processed seed oils such as soybean oil, corn oil, and canola oil are also common ingredients in ultra-processed foods. These oils are high in omega-6 fatty acids, which, when consumed in excess and without balance from anti-inflammatory omega-3s, create an inflammatory environment in the body. Chronic inflammation impairs the function of mitochondria, damages blood vessels, and disrupts immune signaling. It also compromises the skin barrier, leading to dryness, irritation, and premature aging of the skin. Inflammation doesn't just affect the surface. It accelerates wear and tear throughout the entire organism, affecting everything from the brain to the joints. Artificial additives and preservatives, while considered safe in isolated doses, can have compounding effects on gut health and immune function when consumed daily over time. The gut microbiome, which plays a crucial role in immune regulation, hormone balance, and even mental health, is highly sensitive to dietary inputs. Emulsifiers and artificial sweeteners found in many processed foods have been shown to disrupt the diversity and integrity of gut bacteria, leading to increased gut permeability or leaky gut. This condition allows endotoxins to enter the bloodstream, triggering inflammation and contributing to autoimmune reactions and skin issues such as acne, eczema, and accelerated aging. Consuming a diet dominated by ultra-processed foods also reduces the intake of antioxidants, fiber, and phytonutrients that protect against oxidative damage. Whole, minimally processed foods provide the raw materials needed for collagen synthesis, DNA repair, detoxification, and hormonal balance. Without these nutrients, the body becomes more vulnerable to environmental stressors, including UV radiation, pollution, and toxins. Shifting away from ultra-processed foods and toward whole, nutrient-dense options allows the body to enter a regenerative mode rather than one of constant damage control.